This video will focus on the fundamental counting principle. So the fundamental counting principle helps you determine the number of ways something can be done. So if we take that same kind of advertisement that was there on the initial screen, there was an advertisement for create a t-shirt for $5. And there were 5 colors, 4 sizes, and 4 designs that were listed. So how is it that we could determine the number of different t-shirts that could be made? Well, one option would literally be to list all of the different possibilities, list all of the options. So that would consist of something like, number 1, we make a red t-shirt that's small and has a heart on it. We make a red t-shirt in medium that has a heart on it. And we could keep going to the point where we come to, for example, we've got a green t-shirt that's a size large that has a smiley face on it. We've got another green t-shirt that's large. Maybe it has a flower on it. But you could see what happens is that this would take a long time to do. And also it would be hard to keep track of whether or not you'd miss something. Listing all of the possibilities, again, is an option. It could be doable depending on how many different possibilities there are, but in most cases, it's not going to be convenient. So what else could we do to make sure that we are counting all of the different t-shirts that could be made? Well, another option is we could make a tree diagram. So this is another way that essentially writes all of the options out, but in a slightly less tedious way. So for example, we could start with our red t-shirt, and from there we can branch off to each of the 4 sizes. So our small, medium, large, and extra large. And then from there, we would have each of the 4 designs, a heart, a star, a smiley face, and a flower. And they would branch off 4 times from each of those, again, with a heart, a star, a smiley face, and a flower. And we could keep going. And once we got done with the red, we would start with the green, and we would again branch off small, medium, large, extra large, and then all of the designs. And what you could do then is you could go along this outer one and you would count how many final branches there are in the tree. So 1, 2, 3, 4, 5, 6, 7, 8, etc., until you count all of the reds, all of the greens, all of the whites and the yellows and the purples. So again, a little less tedious than listing all the possibilities. It's more systematic. It ensures you're not missing anything. But again, still not super convenient because it's a lot of work. And so maybe there's one other way. And so this is where the fundamental counting principle, or also sometimes called the basic counting principle, comes into play. So this is where mathematicians figured out that, wait a minute, there is a faster and a more efficient way to do this. And so I'm going to call this, or refer to this, if you will, as the blank method. And so I'm going to put 3 blanks here. And I'm going to put 3 blanks because the first one represents the color that I need to choose. The second one represents the size that I need. And then the last blank represents the design that I want. So basically, these are the decisions or the choices that I need to make. The number I'm going to put in the blank will represent the number of options or choices I have for that particular decision. So when I look at color, for example, I have 5 choices for how many colors of t-shirt I could have. When it comes to size, I have 4 different choices. And when it comes to design, I also have 4 choices. If we then multiply those numbers together, that will give us the total number of different t-shirts that could be designed, taking into account the color, the size, and the designs available. So by multiplying those together, we will come up with 80 different possibilities. So let's put the fundamental, or again, the basic counting principle into a little bit of a formalized definition. So what this says is that when there are a series of decisions, or if you will, choices to be made, the total number of ways those decisions can be made is represented in the following way. N1 times N2 times N3 times ... Keep going until you get to the last decision. And I know that notation can be a little intimidating at times, but N1 is representing the first decision I have to make and how many choices I have. The N2 is representing the number of choices I have to make for the second decision. The N3, the number of choices for the third decision, and so on. And K just represents it's the last decision. So in the previous example, N1 represented the number of choices I had for color of t-shirt, which was 5. N2, my second decision, was about size, and so that value was 4. And then N3 was all about the design. Again, the value was 4 because I had 4 choices for design. So don't let the notation bother you, okay? All it's saying is 1, 2, 3, etc. are how many different decisions I have to make. And then the number that I like to put in the blank is how I will say it, is how many choices you have for that particular decision that needs to be made. All right, so let's look at an example here. You buy a new phone that requires a 6-digit password. How many passwords are possible? So one of the first things I notice is that this is a 6-digit password. So essentially, I have 6 different decisions that I have to make. I have to choose my first digit, my second digit, the third, the fourth, the fifth, and the 6th. Okay? For each one of those spots, I can choose the digit 0 through 9. Now notice that is a total of 10 digits because we are counting the 0. So if you pick up your phone or you go to your computer and count the number keys on your phone or on your keyboard, there are 10 of them. Okay? Now, in a password, we can repeat digits. If you want your password on your phone to be 999999, you can certainly do that. Okay? You are also welcome to repeat just once or twice, or you can have completely different digits every single time. But again, we are now looking at how many choices do I have under the given circumstances. And our circumstances right now are we just need a 6-digit password. So for my first digit of my password, I have 10 choices. I can use any of the digits 0 through 9. Once I pick the first digit in my password, I now get to pick the second digit in my password. And again, I have 10 choices. I can pick any number I want. And this will be the case throughout the password creation process. There is no reason that I have to eliminate any given digit. I can repeat as many times as I want. So again, the fundamental counting principle would say multiply all of those together. And so what we will find when you multiply 10 together 6 times is there are 1 million different 6-digit passwords that are possible. Now let's consider an example where we have a quiz that has 10 questions on it. The first 6 questions are true-false questions, and then the last 4 are multiple choice, and they each have options A through E, so 5 choices for each one. How many different ways could a student answer the quiz? Or how many different ways could the answers be turned in? So when we look at this question, we are looking at 10 questions on this quiz. These first 6 questions, I'm going to just kind of delineate between. These first 6 questions are true-false questions. So these are all true-false. That'll go all the way down to here. I'm not going to write them all in. And then these next ones are multiple choice where we have A through E as options, again, for these last 4. So again, what we have to think about is what is the decision we have to make. Okay, so that's what the blanks represent. And the number we're going to put in the blank represents how many choices we have to make that decision. So the first decision we have to make is the first question true or false? And so we have 2 choices or 2 decisions that we could, or 2 choices we have for that decision. We can pick true or false. For the second question, again, we have 2 different possibilities, true or false. And that would be the case for each of the first 6 questions. Now things change a little bit when it comes to question numbers 7, 8, 9, and 10. These are the multiple choice questions, and remember we have choices A through E. That gives us 5 different choices for each of those multiple choice questions. And again, we continue to multiply our way down. Okay, so then it's a matter of grabbing your calculator and figuring out what that result happens to be. 1, 2, 3, 4. All right, and assuming I just typed that all in correctly, I am getting 40,000 different possibilities. 40,000 different ways that you could answer the questions on that quiz. Right, for our next example, we are at a restaurant and it features a special. I'm sure you've seen restaurants or commercials where something like this has happened. For $20, you can get an appetizer, an entree, and a dessert. But when that happens, they usually have a special menu, if you will. These are the different entrees and desserts and appetizers you can choose from and get this deal. So the question we're going to ask is, how many different meals are possible? So again, we need to think about what are the decisions we have to make. Well, we have to make a decision about the appetizer we want. We're going to make a decision about the entree we want. And we're going to make a decision about the dessert we want. And from here, what we need to then do is figure out how many choices we have for each of these different decisions. So when it comes to appetizers, we have 4 different choices. Entrees, 7 different choices. Desserts, 3 different choices. And when we multiply those together, we will come up with 84 different meals that could be ordered. Okay, so for our last example that we're going to go through, this is a 3-parter. So let's say we have a password that consists of 5 digits. Now I'm going to put some stipulations on the password. So what would happen if the password that we create cannot have any repeated digits? So again, it's a 5-digit password. So here are the different options that we've got. And now we need to think about how many choices do we have for each one of those positions in our password. So whenever we start, we have, again, the digits 0 through 9 all available to us. So we would have 10 options for the first digit. But we're not going to repeat a digit. So once we've used a digit, imagine throwing that digit out. Okay, maybe you have some little, I don't know, chips with numbers on them, or like Scrabble tiles, if you will, but they're digits instead of letters. Once we use that number, we're going to toss it out. Okay. That would leave us with 9 numbers left that we could use for the second digit. And then we're going to toss that number out. That would leave us with 8 numbers left for the third spot, 7 numbers that we could choose for the fourth spot, and 6 numbers that we could choose for the fifth spot. Again, not doing any repeating of digits. That would give us 30,240 options. Okay, well, let's change it up a little bit. What if our 5-digit password contains only even digits? So I'm going to use an E representing that it has to be even. Now, notice this does not say that we can't repeat. Okay, this is kind of like a restart, kind of pretend that that first question wasn't there. This is like a restart. So we have a password consisting of 5 digits. How many passwords contain only even digits? All right, so one of the first things is we need to count how many even digits there are. So 2, 4, 6, 8. Now, notice that 10 is not a digit. 10 requires the 2 digits, 1 and 0, to make a 10. So 10 is not a digit. However, 0 is considered even. Okay, if you think of skip counting, if you will, for being even digits, if you were to count backwards, 8, 6, 4, 2, 0 is even, and then -2, -4, etc. So 0 is an even digit. So the question is if this first position in our password has to be an even digit, how many choices do we have? Well, we have 5 choices. It could be 0, 2, 4, 6, or 8. Okay, for the next number in our password, the next digit, again, we want it to be even, and it does not say we cannot repeat. Okay, it does not say no repeated digits. So once again, there are 5 different even digits. That would be the case for the 3rd digit, as well as the 4th, as well as the 5th. And so when we multiply all of those 5s together, we get 3,125 different passwords that could only contain even digits. Okay, last but not least, we're going to look at how many passwords would have the number 8 as the last digit. So 1, 2, 3, 4, 5 blanks again for the 5 digits in our password. So notice what could happen here is that this number can be anything we want it to be, as can the 2nd and the 3rd and the 4th, but this number must be an 8. So working through this, the first digit can be anything we want it to be. It can be any of the digits 0 through 9. That gives us 10 choices. The next digit can be any number, again, 0 through 9. That's another 10 choices. Same thing for our 3rd digit. Same thing for the 4th digit. But that last digit must be an 8. Now, I'm going to caution you, okay, the number that goes in the blank, the number I want to multiply together with this string of 10s is how many choices I have. Okay, if the number must be an 8, I only have one choice. Okay, don't put an 8 in the blank. You don't have 8 different options. The number has to be an 8. That means you have one choice. Okay, so we're going to put a 1 in the blank. And again, multiplying all of those together gives us 10,000 different 5-digit passwords that have the characteristic the 8 is the last digit.